Hi students, this is our last topic in second PUC, that is semiconductor electronics. Here we know that matter is divided into three types as solids, liquids, gases. We studied this so many times. But according to the electrical conductivity, solids can be divided into conductors, insulators and semiconductors. So what are these semiconductors? Germanium and silicon, which are available in the fourth A group of our periodic table, are known as semiconductors whose valency is 4. So valency of these semiconductors is 4. So actually this germanium silicon actually revolutionized this field of electronics. So this is a great revolution here. These two revolutioned the entire field of electronics. What is that revolution? In 1948, when they discovered this transistor, so which is the basic building block of this integrated circuits, ICs. So due to this transistor only, they were able to produce this portable radio. Previously the size of the radio was too huge, but afterwards it was made portable. It can be carried from one place to another place. And also these recorded players, tape recorders, as well as computer industry also. We know that the size of the first computer made almost occupies a big room. But now we have computers which can be foldable computers and which can be kept in our pockets also. So this is because of the invention of these transistors and also these integrated chips. Now in 1930s, the solid state semiconductors, what are the main points that were discovered in these solid state semiconductors, that is in germanium and silicon? The first one is possibility of controlling the number of charge carriers. So semiconductors can control the number of charge carriers in a body, and also they can change the direction of the charge carriers. So after observing these two important points, so scientists tried to use these semiconductor devices. Now why we are using these semiconductors in place of conductors here? They are small in size, consumes low power compared to the conductors, operate at low voltage, have long life and have high reliability also. Because of these points, we are replacing these conductors with semiconductors. Previously, if you see the old TVs, the size of the picture tube was too huge. Now we have TVs, slim TVs. Now what is the main component there? That is cathode ray tube was used previously in big TVs as well as in big computers. But now we are using liquid crystal display TVs, LCD TVs. So LCD TVs uses these transistors only. Now whenever this germanium or silicon are excited, so excitation may be by using light energy, by using heat energy, even a small electric voltage can change the number of mobile charge carriers in germanium and silicon. So due to this small light energy, small heat energy and small voltage, we can change the number of charge carriers. So N can be increased very rapidly. Due to this, these semiconductors are very useful in this electronic field. Now here, solids actually divide into crystalline solids and amorphous solids. Crystalline means these are sugar, salt, these are all crystals. So they have regular pattern. But amorphous solids, they have no regular pattern. This is about the regular pattern or non-regular or irregular pattern of the arrangement of the atoms inside a solid. But according to electrical conductivity, electrical nature, solids can be divided into conductors, insulators and semiconductors. In conductors, the resistivity falls from minus 10 power minus 2 to 10 power minus 10 ohm meter. And for insulators, resistivity is from 10 power 11 to 10 power 19 ohm meter. But semiconductors, resistivity lies between conductors and insulators. As well as the conductivity of semiconductors also lies between conductors and insulators. So conductivity is less than say conductors and more than insulators. Now what is the resistance of a conductor that we studied in current electricity? R is equal R naught 1 plus alpha delta T, where alpha is a temperature quotient of resistance. So alpha is positive for conductors, means if the temperature increases, resistance of conductors also increases. but if temperature increases, resistance of insulators as semiconductors will decrease. So, to have more conductivity, we need to decrease the resistivity. To decrease the resistivity, we need to decrease the resistance. To decrease the resistance, we need to increase the temperature. So, by heating these semiconductors, we can increase the conductivity. So, the resistance of a semiconductor is given by R is equal to A e power minus B by T. So, resistance decreases exponentially with the temperature, where T is the temperature, A and B are constants here. So, what are these semiconductors? Semiconductors, here one more point is, conductivity can be increased by adding small amount of suitable impurity also. So, that we will discuss later. So, here 2 points, how to increase the conductivity. To increase the conductivity, we need to decrease the resistivity, we need to decrease the resistance. So, resistance can be decreased by increasing the temperature. So, one of the method of increasing conductivity is increasing temperature, and one more method is adding suitable impurity. Now, we have different semiconductors, germanium, silicon. These are called elementary semiconductors. Previously, we were using germanium, but nowadays we are using silicon. Why? Because this is abundantly available in the nature. So, as it is abundantly available, so we are making almost these transistors, diodes with silicon only. That's why our Bangalore city is also known as Silicon City. Why? Because there a lot of electronic industries were developed. Then we have this cadmium sulfide, lead sulfide, and gallium arsenide. These are called compound semiconductors, and nowadays we are using these also for manufacturing these transistors, diodes, or electronic devices. Energy band in solids. If you take an isolated atom, for example, if you take sodium, so we have written this electronic configuration in lower classes as 1s2, 2s2, 2p6, 3s1. That means in s orbital we have 2 electrons, in 2s orbital we have 2 electrons, in 2p orbital we have 6 electrons, and 3s we have 1 electron. So, the electrons which are in 1s have some energy, and the electrons in 2s have some more energy. Electrons in 2p have a different energy here, and a lone electron in the 3s orbit will have different energy. For an isolated atom, electrons in different energy states will have different energy. So, these are orbits or energy states. Now, suppose if you take sodium atom here, this is sodium atom, but if you take a sodium element, sodium material, some material, so here we have so many atoms. So, when large number of isolated sodium atoms are brought together, so there is just so many various interactions between these. So, due to these interactions, what happens? The energies of these electrons which are available in these orbits will change. But it is found that the energy of electrons in the inner orbits of an atom remains as it is. So, they are not changing here. But the electron which is available in the outermost or higher energy orbit, outermost orbit means higher energy orbit. We know that energy is least in the first orbit, and energy increases if you go away from the nucleus. And as this electron is away from the nucleus, so it will this will be influenced by other interactions here. That's why its energy may vary and it changes from state to state. So, the outermost orbit will have different energy states, and here it can be divided into 3 types. One is a valency band, other one is a forbidden gap or forbidden energy band, and the last one is conduction band. If electron is available here in the lower energy state, this is only single energy state only, that is the 3s only here, but there will be some split levels of energies here. So, this electron may have this much energy. If the electron is available in this energy band, that is a range of energies possessed by electron, this is called, this is said to be valency electron. If electron jumps here, then it is said to be conduction electron. That means in the 3s orbit only, electron may have different energy states. But for an isolated atom, electron in a particular orbit will have constant energy. But here it may have the range of energies. If energy is in this 3s orbit, if energy is least, then it is said to be in valency band. If energy is intermediate energy, then it is said to be in a forbidden energy band. Forbidden energy band. If in 3s orbit, if the electron is possess more energy, then it is said to be in conduction band. So here highest energy, if electron in the 3s orbit has highest energy, then it is said to be in conduction band. That means for any electron which is in the valency band, for this to conduct electricity, it should jump to that highest energy band within that orbit only. So this jumping is called excitation. So this can be achieved by supplying light energy, or by supplying heat energy, or by supplying a small amount of voltage. So how to excite these electrons from valency band to conduction band? So that we will discuss here. Before that, here if you see these conductors, semiconductors and insulators, here we have seen this is valency band, this is conduction band. Energy of conduction band is greater than energy of valency band. Now in conductors, you can see this is the valency band. So if it is the total band, this is the valency band, and this is the conduction band. This is the conduction band. So what is the meaning of this one? In conductors, if one electron is present here, so it is said to be in valency band, its energy is less. If electron is present here, this is in both valency as well as conduction band. If energy is slightly more, so it can behave as a valence electron or conduction electron. If it is having more energy here, then it is said to be in conduction band. That means both valency band and conduction band overlap with each other in conductors. But in semiconductors, so this is the conduction band here, this is the conduction band, and this is the valency band here, this is the valency band. So this is a valency band, this is a conduction band. So here there is a small gap between conduction band and valency band. So this gap is called a forbidden gap, and here the energy of that forbidden gap is around 1 electron volt. So energy from this electron will differ by around 1 electron volt here. So if you supply that 1 electron volt, it will jump into conduction band. So how to supply that energy? We will supply light energy, heat energy by supplying electrical energy, or even by adding impurities also we can increase the number of electrons in the conduction band. That we will discuss later. Now in case of insulators, this is the conduction band, very thin one, and this is the valency band, and this is the forbidden energy gap. The energy gap is nearly 6 electron volts or greater than 3 electron volts. So this is the valency band, this is the conduction band. So valency band and conduction band are separated by a large gap, are separated by a large gap here. Types of semiconductors. We can divide the semiconductors into germanium, silicon or gallium arsenide. All these semiconductors can be divided into two types. The first one is intrinsic semiconductors, second one is extrinsic semiconductors. So intrinsic semiconductors, actually these are the pure semiconductors. Semiconductors in their pure form are called intrinsic semiconductors. Here you can see, let me take a germanium here. Each germanium atom is making a covalent bond with another germanium atom. So each germanium atom will form 4 covalent bonds here. So these are the electrons here, these are the outermost electrons for this one. So each outermost electron will be having a covalent bond with another electron in the neighboring germanium atom. So here there exists a covalent band between these valence electrons. So this is the purest form of germanium. Here you can see the valency band have electrons here. So I am going to write the valency band, these are the electrons here. So when the at room temperature, the valence band is filled with electrons, but there are no electrons in the conduction band. That means germanium at room temperature acts as an insulator only. Now, if you supply some energy to this one externally, then some of the electrons in the valence band jump to the conduction band. Let us say it jumped to the conduction band, so it will form a hole here. That is a deficiency of electron or deficiency of negative charge. So deficiency of electron is called hole. Which acts as a positive charge. So if two electron jumps from here to here, two holes will be formed here. That means in a intrinsic semiconductor, the number of holes formed is exactly equal to the number of electrons in the conduction band. If two electrons jumped here, two holes will be formed. So number of holes is equal to number of electrons. Now, if this is connected to a battery or cell, or a electric field is applied between the two ends of this germanium crystal, if this is positive or negative, then what happens? The holes will move in the direction of the electric field. Holes will drift in the direction of electric field, whereas these free electrons will drift opposite to applied electric field. So let us say this is the crystal, this is the positive plate and negative plate. Electric field is from left to right. Now the holes will move towards the right side, electrons will move towards left here. So the total current in a pure semiconductor or intrinsic semiconductor is given by current due to holes plus current due to electrons. In a conductor, current is only due to the flow of electrons, but in a semiconductor, current is due to both holes as well as electrons. So this is the total current in a pure or intrinsic semiconductors. But remember students, at room temperature, a pure or intrinsic semiconductor always acts as a, so pure germanium or silicon acts as insulator. Reason is there are no electrons in the conduction band, but electrons will be available in the conduction band only if the electron in the valence band jumps from here to here. Now we will come to the second type. This is extrinsic semiconductors, also called impure semiconductors, also called doped semiconductors. So first of all, what is this doping? Doping is the addition of impurities, suitable impurities, to increase the conductivity of a semiconductor. Here the conductivity of pure semiconductors is generally less, and it can be increased by addition of this, by increasing the temperature here. But here in case of extrinsic or impure or doped semiconductors, we have two types of impure semiconductors. One is P type, other one is N type. Here in a pure germanium only, we can add a trivalent impurity, that is a trivalent, valency 3, trivalent impurities like aluminum, indium, gallium, thallium. So these are the trivalent impurities including boron. As germanium is similar to this group, that means if the size of the germanium is nearly equal to size of some other atom, here aluminum and silicon size are equal, and indium and germanium, this is 13 and 14, atomic number 13, atomic number 14. So for silicon, generally we use aluminum as the impurity. For germanium, we will use indium as the impurity because atomic size are equal. So here, when indium is added to germanium crystal in its crystal manufacturing stage, then I am adding indium here. Indium has a trivalent, means it has only 3 electrons in its valency orbit. So here I am showing this indium has 3 valence electrons, whereas germanium has 4 valency electrons here. So each germanium has 4 valence electrons. Even here also, each germanium has 4 valence electrons in its outermost orbit. That's why I am showing 4 electrons here, and each and every one is having a covalent bond with the neighboring germanium atoms. But here, indium has only 3 valence electrons. So it will form a covalent bond with this germanium, with this germanium, with this germanium. But for this electron, there is no electron to have this covalent band. So there is a deficiency of electron. So this deficiency electron we call it as a hole. So whenever one indium atom is added to germanium crystal, one hole will be formed. If you add 10 indium atoms, you will have 10 holes. If you add n indium atoms, you will have n holes in this germanium crystal. So here, if you draw the graph, that is conduction band and valency band. At room temperature, valency band will have electrons here. But conduction band is empty. But when we add this one, what happens? One hole will be formed here. Whenever a hole is formed, one electron will be formed here. So here, by heating this one, some holes will be formed here. These are the holes formed due to heating, and some more holes will be formed due to addition of these impurities. So number of holes will be more here. So these are the holes due to increase in temperature, because electrons here jump to the iron orbit. But these are the holes which are formed due to addition of this impurity. So here what we can say, in p-type semiconductor, number of holes are greater than number of electrons. But once again I am telling here, whenever a hole is formed due to electron that is jumped into this conduction band, so this is called regeneration of holes and electrons. But here reunit, that means some of the electrons will combine with this one. If 3 holes are formed, 3 electrons may occupy this space. So regeneration and this reproduction may be equal due to this conductivity may be less in this case also. Now, if you take this n-type here n-type here we are adding trivalent impurity, and if we add a pentavalent impurity, now pentavalent impurity means atoms having 5 electrons in its outermost orbit, that is nitrogen, phosphorus, arsenic, antimony, bismuth. Once again, as it is germanium, generally we will add arsenic. For silicon, generally we will add phosphorus, because their atomic numbers are equal, nearly equal, and their atomic size are also nearly equal. But here, if you add arsenic here, so each and every germanium atom has 4 electrons in its outermost orbit. But arsenic, as it is pentavalent, has 5 electrons in its outermost orbit. 1, 2, 3, 4, one more extra electron. So now what we can write? This is the conduction band, and this is the valency band here. So valency band has electrons at room temperature also. Whenever its temperature increases, what happens? Some of the electrons jumps to the conduction band. So here holes will be formed. 2 holes are formed because of the 2 electrons that are jumped from valency band to conduction band. But as it is doped with this arsenic, some more electrons are formed here, but holes will not be formed. So in this case, number of electrons are greater than number of holes formed here. Due to this, the Fermi energy level is very nearer to the conduction band for n-type, and Fermi energy level is very nearer to the valency bond here. Fermi energy level means highest energy level obtained by this electrons. So this is nearer to this valency band because more holes are available here. Here as more electrons are available here for conduction, Fermi energy level is very nearer, close to this conduction band. A pure silicon at 300 kelvins, 300 kelvins means 27 degrees Celsius. Generally we take it as room temperature has equal electron and hole concentration of about 1.5 into 10 power 16. So this value is called Ni, which is equal to 1.5 into 10 power 16. Number of charge carriers in an intrinsic semiconductor, that is pure semiconductor, is this much. Now, when it is doped by indium, this NH increases to this much. So NH is equal to 4.5 into 10 power 22. So what is Ne? It is found that the product of the number of holes formed into number of electrons formed in a doped semiconductor is equal to square of the number of charge carriers in a pure semiconductor, that is intrinsic semiconductor. So here NH is 4.5 into 10 power 22. We are finding Ne, which is equal to 1.5 into 10 power 16 whole square. So this 4.5 can be written as 9 by 2 into 10 power 22 into number of electrons is equal. This is 2.25 into 10 power 32. So you can write this Ng as this 2.25. This can also be written as 4.5 by 2 or 9 by 4 into 10 power 22 divided by 9 by 2 into 10 power, this is 32, this is 22. You can cancel 9 and 9 here. This is 1 by 2 and goes up 2 by 4 into 10 power 32 minus 22 will be 10. This is 1s and 2s. So this will be 0.5 into 10 power 10 or 5 into 10 power 9 here. So this is the Ng value, that is number of electrons here. Number of electrons available on a doped silicon. Here, charge carriers in a semiconductor. Now let me consider a semiconductor of cross-sectional area A and length L here. So this is the length of the semiconductor and it consists of so many charge carriers, and due to thermal agitation these charge carriers generally moves in all possible directions randomly. But if it is connected to a battery or if electric field is applied between these two, then they will have a particular direction of motion. Here, what are the total charges here? Let us say N is the number of charge carriers per unit volume. So this I will take as Nc here. Now we can write current I is equal to Q by T, that is a number of charge carriers per unit volume into volume of this one is A into L into E by T. So this L by T can also be written as the drift velocity of this charge carriers. So I can be written as N E A V here. So this is the current equation that already is derived in current electricity. But we know that this drift mobility is the drift velocity produced for unit electric field. So in place of velocity I can write I is equal to NEA. In place of velocity we can write mobility into electric field. So this is another equation for finding the current through a semiconductor. Now we know that the electric field and resistivity as well as this conductivity related as sigma is equal to J by E, where J is called current per unit area into E. So sigma is equal to, we got the current formula here, N E A mu E by A into E here, cancel E and E here, A and here. So this is the conductivity here. So the conductivity of charge carriers or semiconductor is given by sigma is equal number of these charge carriers that I am denoting with the NC here, number of charge carrier per unit volume into charge of the charge carrier into mu here. So this is the conductivity. So as we know that semiconductor consists of both holes and electrons, the net conductivity or total conductivity is given by sigma is equal sigma holes plus sigma electrons. So sigma is equal, what is sigma holes? So this you write number of holes into charge of each pole into mobility of hole plus number of electrons into charge of electron into mobility of electrons. This is the total conductivity of a semiconductor device. In a PN junction diode, when a P-type is connected with the N-type joined together, first of all, P-type holes will travel from here to here due to concentration difference here, concentration gradient. Similarly, the electrons will travel from N side to P side here due to this concentration gradient here. So this is called diffusion. So whenever a PN diode is formed, here the holes are diffused from left to right. So this is called holes diffusion, which takes place from P to N side, and electron diffusion will takes place from N side to P side. So this is a electron diffusion. So after that what happens? Here we are left with when all these most of the holes travel from here to here, we will have only negatively charged ions here because positive charges are moved from here to here. Similarly here positive charged ions will be formed. So these are immobile ions. So due to this here we will have a region which is called depletion region layer between these two. So here you can see this is at high potential, this is at low potential. So a potential difference will be formed between these two ends of this junction, and this is called a potential barrier which acts from N to P side. So this is, that means this is at high potential, this is at low potential. This potential barrier will not allow any further movement of the charge between P and N side. But due to this what happens? Here if an electron is formed here, we know that positive charge will move in the direction of the electric field. This is the direction of the electric field here. So positive charges will try to move in this direction. This is called drifting of positive charges. Here holes are diffused here. Here holes are drifting. So here holes will drift here. Holes drift here, drifting of holes. And electrons will move in the opposite direction of the electric field. So electrons will drift here. So as a whole, in a PN diode, we have two currents. One is a diffusion current. Second one, drift current. So the current in any PN junction diode is due to diffusion plus drift current. PN diode can be divided into two different types or different modes. One is called a forward bias. The other one is called a reverse bias. In forward bias, what happens? PN diode, generally we denote a diode like this, and this is a P side, this is N side. So this is the PN diode. If P side of the diode is connected to positive terminal of a battery, N side is connected to negative terminal of the battery, so then what happens? The thickness of depletion layer decreases in forward bias. Thickness of layer decreases, and resistance, as the thickness decreases, here resistance also decreases, then flow of charges takes place. So current flows here. As the resistance decreases, current flows through the diode. Now similarly in a reverse bias, if a diode is connected such that P type connected to negative terminal and N side connected to positive terminal of a battery, then this is called reverse bias. Here thickness of depletion layer increases, thickness increases, resistance increases, so current decreases and current may become 0 also. Generally no current flows through this diode. And most importantly in competitive exams, they may give this problem. See, this is a diode. These are the 4 diodes, and which of them are connected in forward bias? Most frequently asked question here. 10 volts, 20 volts, 0 volts, minus 10 volts. This is a minus 10 volts. This is 40 volts. This is 10 volts. This is 0 volts, like this. So which of the following are connected in forward bias? Every time P should be connected to positive terminal or high potential, N should be connected to negative terminal or low potential. Here in the first diagram, P connected to 10, N connected to 20, so N is connected to high potential. So this is not forward bias, this is reverse bias. Here this is 0, this is minus 10. So 0 is bigger than minus 10, so this is the forward bias connection. Similarly here this is minus 10, this is 40. So low potential, this is high potential. This is also not forward bias. Here this is 10 volts and 0 volts. So P is connected to high potential, N is connected to low potential, and this is also forward bias. Characteristics of a diode. Here I am taking forward bias voltage along x-axis and forward bias current which is measured in milliamperes along y-axis, and reverse bias voltage along negative x-axis, and reverse bias voltage also called leaking current along negative y-axis. But this is a microamperes, very small current. Now here what happens, for germanium the barrier potential voltage is 0.3. That means if the applied voltage is 0.2 or less than 0.3, then no current flows through a diode. Let us say this is 3 volts and this is germanium. So germanium has a barrier potential voltage of 0.3. If you apply 0.1 volts of battery here, then no current will flow even though it is in forward bias. Why? Because for this current to flow from P to N side, the minimum voltage required is 0.3, that is the junction voltage or the voltage between the two junctions or two sides of the junction, two edges of the junction. Now if it is 0.2, then also no current will flow. If it is 0.3, then also no current will flow. If you make this voltage as 0.4, then the potential difference between this one is applied voltage minus barrier potential voltage, which is equal to 0.1. If you know the resistance of this diode, then we can find the current as this applied voltage minus barrier potential voltage by resistance of the diode, which is equal to, in this problem, 0.4 minus 0.3 by, let us say resistance is 10 power minus 3 or 10 ohms here. So this is 0.1 by 10. This is 100 by 10 amperes. So this is how we can find the current. That means if the voltage is less than the barrier voltage, no current will flow through the diode even it is in forward bias. That's why here I am showing for silicon this is 0.7 volts. So here you can see the current is denoted along y-axis. Here current 0, 0.30, 0.40, 0.50, 0.60. At 0.7 current is rising. So this is a VI characteristic curve for a silicon diode here, silicon diode. So now after that current start increases. Now the current at which current increases in forward bias is called knee voltage also. Now this is about forward bias. After this knee voltage, it behaves as a conductor only. Now in reverse bias what happens, this is not in milliamperes, this is in microamperes, very small current. Actually no current will flow through the diode, but due to thermal agitation, the minority charge carriers, that is in P type, the minority charge carriers are electrons, and N type, the minority charge carriers are holes. So these electrons and holes will be accelerated by the applied electric field. When the electric field is nearly 20 or 25 volts, this 25 volts is enough here after 3 volts, because while drawing this diagram, the conduction band as well as valency band, the gap is more than 1 electron volt. If it is 3 electron volts, then for this 1 electron volt means 1 volt into 1 electron. So these electrons will have this much energy. 1 electron volts, the potential difference between the two ends is, of the diode is 1 electron. If it is 3 electron volts, this energy will be 3 electron volts. So almost all the electrons in the valence band jumps to the conduction band. That's why it behaves as a conductor after this 3 volts here. But here when the applied voltage is around 25 electron volts, most of the covalent bonds will be break, and due to this conductor, this diode will be ineffective here, then large current flows through this one, and that particular voltage at which this diode will break is known as avalanche breakdown.